Hey everybody. So I've mentioned a couple of times in previous videos, since we're approaching trigonometry from the perspective of circles, um, you may have already seen it from the perspective of triangles, and I've insisted that this perspective still is true. It's just more limited. And so the subject of this video is the subject of this is that we're going to make that connection. How do we? And we've already hinted at it, so you may have already seen how the connection works, but let's make it really explicit. So I've drawn here a picture that we have seen countless times already. So we've got our unit circle and an angle theta, and or at least a piece of the unit circle, our angle theta, with coordinates x, y. So I want to do what I've done before and drop a vertical line, more or less. Let's make this a little thicker. Drop ourselves a vertical line here, and having trouble staying straight today. So if we look at this triangle, this side of it is x, this side of it is y, right? The same as those coordinates there. Oh, and let's put in our definitions of our trig functions via the circle, which is cosine of theta is the x coordinate, sine of theta is the y coordinate, tangent of theta is y over x, and then of course we have the reciprocals of these. Cosecant theta is 1 over y, and cotangent theta is x over y. Okay, so there are our 6 trig functions. So now let's grab this triangle. I think I have to grab the whole. Wait, let's make sure I get this and copy, paste, and I'll just erase the parts I don't need. Okay, so now what I'm pulling out is just that triangle. Okay, and so before we go too far, it might be obvious right now that we can, I'll put in one more. Oh, it looks like I accidentally erased that circle, but that's fine. We can take this triangle and define the trig functions based on this triangle that I pulled right out of the unit circle. But a bigger question would be, can we do this for triangles that don't fit into the unit circle? Okay, well, let's see what happens if we do. Let's say I have a triangle like a right triangle, except it wouldn't fit in the unit circle. Let's say it's a scaled version of this. So I'll copy this again. Oops. But this time we'll scale it. All right. So if I've scaled it, whoops, sorry, I'm having trouble using this thing today. If I've scaled it, let's say I've made it c times bigger, then each of these sides will scale by a value of c. So this hypotenuse, which was 1, becomes c. This height that was y will be c times whatever y is. And this base that was x units long becomes c times x. Well, let's examine what probably are familiar definitions of the trig functions with this scaled triangle and see what we get. So for instance, if we take as our definition of the cosine of theta to be the adjacent side over the hypotenuse, and I'll clarify, well, let's just clarify this now. What do I mean by the adjacent side? Well, when we've got a right triangle, there are 2 angles that are not the right angle. If we are, so we're talking about theta in this case. The side adjacent to theta is, there's 2 sides that define theta, right? These 2 sides on either side. One is the hypotenuse, the other one is the adjacent side. So it's the side that helps form theta that's not the hypotenuse. And the hypotenuse, of course, is the one across from the right angle. So the adjacent side has side CX. The hypotenuse has side C. Those C's cancel, and we get that the cosine of theta is X. Okay, and so this is the definition of trigonometry of cosine that most of us probably learned the first time we saw trigonometry, and it agrees with what we have here. Sine of theta is going to be equal to the opposite side over the hypotenuse. The opposite side is the side across from it. So in this case, that has length cy over c or y. The tangent of theta is going to be the opposite over the adjacent. This will be cy over cx or y over x. Let's just go through the rest. Secant of theta will be hypotenuse over adjacent, c over cx or 1 over x. Cosecant of theta will be the hypotenuse over the opposite, c over cy or 1 over y. And cotangent theta is going to be the adjacent over the hypotenuse, which is going to be cx over cy or x over y. So with these perhaps more familiar definitions, we see that the exact same values will emerge that we got when we dealt with this in terms of the unit circle. Okay, so they're still correct. Remember what I said, these definitions are correct. They're just limited, right? With right triangles, we don't have angles bigger than 90. We don't have negative angles. We certainly don't have angles that incorporate going around several times. But when we're dealing with triangles, the geometry of the situation, this adjacent over hypotenuse, these different ratios of side lengths are still 100% true and don't in any way negate or conflict with the circle definition that we came up with. Let's also look in the other direction, or at least intuitively look in the other direction. What I mean by that is, if we start with a right triangle, so let's start with a right triangle, maybe something like, see if it does it for me. Nope, I gotta be better than that. I missed again. I'm really having trouble with this thing this morning. Sometimes I'm gonna blame it. All right, that looks pretty good. There we got a right triangle. Here is our right angle. And let's put an angle, let's look at this angle theta. Okay, and let's give some names to these, A, B, and C. For instance, let's look at the sine of theta. That would be the opposite, the side across from theta, over the hypotenuse. Okay, well, let's see if this still makes sense. Now I took something from the unit circle and turned it into a triangle. Let's take this triangle and see if we can force it into the unit circle somehow and not have it conflict with what we've done so far. All right, so let's get a circle in here. That looks more or less centered, I think, maybe there. Okay, so here's our unit circle. Let's copy, paste, and now let me rotate this thing around. Oh, shoot. Oh, I am really off today. Sorry, folks. Let's try that again. There's our paste. All right, so now I'm going to rotate it around. Everything's upside down, but that's all right. Let's move it, putting the at the origin. We'll have to eyeball this a little bit. That looks pretty close. Okay, so we've got now a scaled version of our triangle, right? So these side lengths, well, we know to scale it into here, this hypotenuse, which was length C, now has to be length 1. Let's get it a little closer, right? Because to fit in the unit circle, this hypotenuse length C has to now be length 1. So we'll put that in. But that means this side, every side is getting scaled by 1 over C. This side here will be A over C. Well, that means that the X coordinate is B over C and the Y coordinate is A over C. So the sine of theta by this unit circle definition is going to be A over C, which is exactly what we got when we were looking at a triangle that didn't have to fit into the unit circle. So we're just scaling the triangles, which doesn't change anything about the ratios. If you don't believe me about that, just imagine holding a triangle really close to your face and then moving it far away. Nothing would change about the relationship of the sides. If one side was twice as long as the other one was close to, when it looks much smaller further away, that side's still going to be twice as long. Okay, so this is as far as we're going to go to prove that this all works out, but it does. They're completely compatible definitions. The one thing we have to be careful of is, as we saw here, the orientation of our triangles. So let's draw one more right triangle with an, let's say, unideal orientation. So maybe I have a right triangle that looks like this. So here's my right angle. I'll call this angle here alpha, and this angle here beta. And let's label the sides across from alpha. I'm going to call it A. Across from beta, I'll call it B. And across from the right angle, I'll call it C. This is a pretty typical way to label things, since alpha is in the Greek alphabet corresponds to A and beta to B. It just kind of is a handy way to write things. We don't have to, but it's a good labeling system. So let's just go through all of the, let's go through some of the trig values for these angles. So the sine of alpha is going to be the opposite over the hypotenuse, A over C. Cosine of alpha is going to be B over C, right? Again, the adjacent side to alpha is the side next to it, or that contains it, or that helps define it, but not the hypotenuse. And then tangent of alpha will be A over B. Okay, let's look at let's do the cosine of beta. Cosine of beta, so now I'm here, the adjacent side to beta is the one that contains it or helps define it, which is A, not the hypotenuse. So this is going to be A over C. The sine of beta is going to be opposite B over C. And let's do the cotangent of beta. This is going to be the adjacent over the opposite. That's A over B. Right? And you probably notice something immediately that we'll come back to in just a few minutes. Two things I want us to notice, right? There's two angles in every triangle other than the right angle, and so the trig functions depend on which angle you're talking about. But also we might notice, again, we'll come back to this in a minute, that the sine of alpha and the cosine of beta in this triangle are the same. and say similar relationships for cosine of alpha, sine of beta, tangent of alpha, cotangent of beta. So we'll come back to that notion in just a few minutes. Let's first just do some simple examples with these triangle definitions. So for instance, if I have this triangle, there's a right angle. Let's call this alpha. And let's say we know the sides are 3, 4, and 5. Then the sine of alpha would be the opposite over the hypotenuse, right? The opposite is across, the hypotenuse is the one from across from the right angle. Let's just do one more of these. The tangent of alpha will be the opposite over the adjacent, right? So nothing too spectacular there. We can see that we're just using the side lengths to compute these trig functions. Let's do a more useful example, perhaps. Let's look at okay, so I was attempting to draw an equilateral triangle there. I don't think I quite, maybe I can do it one more time. Let's see. Oh, I can adjust it. All right, that looks a little better. Let's use that one. So I'll get rid of this guy. Make it a little bigger. We've got more or less an equilateral triangle. What does that mean? It means all the sides are the same length. Let's make them all side length 2. It also means that the angles are all the same. Remember, the sum of the angles of a triangle have to add up to pi. So if we're taking that and dividing into 3 equal angles, they're each going to have a measure of pi over 3. I'm just putting 2 in because we're doing right angle trigonometry. We don't have a right triangle. But if I drop this vertical line so that it's perpendicular with the base, notice that I have split this top angle in 2 by symmetry, which means it's half of pi over 3 or pi over 6. So we've got this nice little triangle here. It's also going to split the base in half. So the base was a total of 2, but now this side of it is only 1. So first, let's find the height of this perpendicular we dropped. Well, we're going to use another piece of right triangle geometry. When we have a right triangle like this, we know that the sum of the squares, the Pythagorean theorem, the sum of the squares of the lengths of the sides. So in this case, that's 1 squared plus h squared has to be equal to the hypotenuse squared. So that's the 2 squared is 4, which means h squared is equal to 3. H is got to be plus or minus 3, but we're dealing with lengths, so we're going to call them positive. So h is now the square root of 3. Let's just put that in. Okay. Now, with this triangle in mind, let's compute some of our trig functions. So for instance, the sine of pi over 3, looking at this angle here of pi over 3, sine is opposite over hypotenuse, root 3 over 2. And let's look at the sine of pi over 6. Now I'm looking at the opposite of this angle, 1 over 2. Okay. Let's also look at the cosine of pi over 3. This is going to be the adjacent side to pi over 3, which is the 1 over the hypotenuse. And the cosine of pi over 6 will look opposite that pi over 6 angle. Sorry, adjacent to that pi over 6 angle is the height, which is root 3 over 2. Okay. Now, you might notice that these are some numbers that show up on our unit circle. Let's do a quick sketch of that. For instance, when we have an angle of pi over 6, we get this intersects at the point root 3 over 2, 1/2 on our unit circle. There's our cosine of pi over 6 and our sine of pi over 6, right? And what you might realize is this little triangle, let's do it in another color, right here, is a scaled version of this half of the triangle with the pi over 6 angle placed at the origin, right? So we'd have to flip it around a little bit and put it in there, but that's that same triangle. And we see those same values emerging. If we look at the angle pi over 3, right? This reverses. That point up there, that point now is 1/2 root 3 over 2. We've taken this triangle now and put this corner with pi over 3 at a scaled version of this triangle. In this case, scaling it in half to make that hypotenuse equal to 1. We've put that at the origin, and we get those same values of sine and cosine with that definition. So we see we can go from triangles to circles and back and forth without any loss of no conflicts, right? The one place where there can be a conflict is if we're using the geometry of triangles, but we're not dealing with something in the first quadrant, and we'll do examples of that in later videos. But we have to think about the sign, not sign the trigonomic function, but whether things are positive and negative. If, for instance, we had this same triangle in here, that 1/2 now is in the negative direction, right? So that's the one little place where they disagree, because with triangles, we will only deal with, we're dealing with distances that we think of as being positive, whereas on the coordinate system, we have direction that matters. Okay. The other thing I want us to notice again is what I pointed out a minute ago. We have these interesting relationships here. Oops, I circled the wrong two things. That the cosine of pi over 3 is the same as the sine of pi over 6, right? So notice that these two things are the same, and these two things are the same. Okay? And this is no accident. We saw this generally a moment ago, but let's make this very explicit. If we have a right triangle, so I'll do alpha, beta, A, B, C. We see that the sine of alpha is A over C, which is the same as the cosine of beta. Or the sine of beta is equal to B over C, which is equal to the cosine of alpha. Okay. Well, let's notice something else. What do we know about alpha and beta? Alpha plus beta has got to be equal to pi over 2, right? Why is that? Well, we've talked about this before. We know that the entire triangle, the sum of the angles of the whole triangle has to be pi. We've got a right angle, which is pi over 2. So the other two have to have that other half pi, okay? Which is another way of saying that alpha is equal to pi over 2. Sorry, I want to do it the other direction just to be consistent with my notes. There's no problem with what I just wrote, but I want to just be consistent with the text and my notes. Beta is equal to pi over 2 minus alpha, okay? And so these relationships I wrote up here, I can now summarize as follows. Sine of alpha is equal to cosine of beta, but beta is pi over 2 minus alpha. We also get cosine of alpha is equal to sine of pi over 2 minus alpha, right? This is this one. Cosine of alpha is sine of beta, but beta is pi over 2 minus alpha. I'll leave going through using this triangle to see these other results, but we also get tangent of alpha is equal to cotangent of pi over 2 minus alpha. We can always go the other direction. Cotangent of alpha is equal to tangent of pi over 2 minus alpha. Secant of alpha is equal to cosecant of pi over 2 minus alpha. And cosecant of alpha is equal to secant of pi over 2 minus alpha. Okay. We call these the co-function identities. I believe I mentioned in a previous video that the identities would come out in this course at a furious pace. And here we go again, another list of identities. Okay. So we see why this is true for triangles, I think, right? We're just, right? The opposite of alpha is the adjacent to beta, right? That's one way to kind of summarize how all of these work. And then the other half of the relationship is that alpha and beta together form an angle of pi over 2. So with those two ideas together, all these different ratios we can manipulate in this way, right? These make our trig functions really handy. All these identities that I'm warning us of means when we encounter trig in the universe, when we're using it to make a model of some little piece of the universe, they're very, let's say, robust functions or flexible functions. We can manipulate them a lot. We can do lots and lots of things with them. So if we have a large amount of algebra or some kind of big computation, we can often use these identities to simplify things, eliminate things, combine different things, which might seem daunting right now, but it turns out to be this really powerful tool that these things have. Let's look at why this is true on the unit circle, or at least give an interpretation of what this is, what we're seeing, how this relates to the unit circle interpretation instead of triangles. So here's our unit circle. All right, let's draw an angle in. Draw something not in the first quadrant, since I'm always drawing it in the first quadrant. So I've got an angle going off here. We're starting there at the terminal side. Let's put it over here. It's fine. Okay. So we'll call this angle alpha. Okay. And let's give it coordinate points. So whatever these values are, I'm just going to call them A and B. Now let's look at another angle. Let's look at pi over 2 minus alpha. But I'm going to draw it in a non-standard way. No, I'm not. No, I'm not. We're just gonna, here's how we'll do it. So I'm gonna draw the initial side here. Okay, so these are on top of each other. There's two different angles here. What is an angle of pi over 2 minus alpha? Okay, that's what we're saying beta is, pi over 2 minus alpha. Well, pi over 2 means I go all the way to here, to the pi over 2, but then I go backwards in the alpha direction. So that means, this gets a little confusing. Maybe I shouldn't have drawn on here. We've got, let's think about what alpha is. Alpha means going pi over 2 plus this little bit, okay? Maybe I'll call this gamma, just to give it a symbol. So there's this little piece of alpha, right? It's the piece that you get after the right angle, after the pi over 2. So if beta is pi over 2 minus alpha. It means we've gone pi over 2 in this direction. When we go minus alpha, we'll go pi over 2 back plus that same little gamma angle, right? Which is going to leave us right here, right? Where this, let's make that one straight. Right, this little piece here that I was calling gamma over here is what we end up with when we get pi over 2 minus alpha. Okay, so, well, in this case, it's going in a negative direction. Okay, so I know it's a little bit confusing, but I'm hoping you can see what's happening here, right? If another way to think about it is if we took this alpha, oh, that makes it more confusing. I'm gonna stop while I'm at least not too far behind, right? So I'll just maybe say it one more time. Alpha goes through pi over 2 and then this little bit more. If instead we start at pi over 2, taking beta to be pi over 2 and then going backwards by alpha, it means we take that pi over 2 right back and then go the same little bit that was left over here, okay? So that this distance in angles here is the same as the distance here, okay? Now, what does that mean exactly? Well, we can, I believe, suss out pretty easily that, so we know just by this triangle and the coordinates here, that this distance here is going to be, I'm going to call it the absolute value of A. I'm just thinking of the distance right now, not the fact we know it's going to be negative. The height here is going to be B. B is already a positive number since it's above the x-axis. We know A has to be negative based on how I drew it, okay? Well, let's think about this little triangle that we get on this side. Okay. The side opposite, let me actually draw this way. Sorry, I should have drawn this over here. The side opposite, if I think about the red triangle right here, the side opposite gamma, right? The side opposite here is this absolute value of A. That's going to be the same length as the side opposite. We've said this angle here is equal to gamma. It's in a different direction than the way I drew it, but it's the same amount of angle. So opposite this must be the same distance, right? And then adjacent to gamma, which is this vertical line here, is now the horizontal line here, has to be a distance of B. Okay, I know this is getting pretty ugly, but it is what it is. Looking at the coordinates now, I know the x coordinate here is this horizontal distance, which is B. I know the y coordinate has a value of A, its size is A, and it's in the negative direction, just like A was in the negative direction here, so it's just A. Right, that's what this new coordinate is. And let's look at the trig functions. Sine of alpha is B cosine of beta, which remember is, well, I'll just write it as pi over 2 minus alpha, which is where we ended up after all this work. The cosine is the x coordinate, which is the same as the y coordinate for alpha. Similar, in a similar way, if we take the cosine of alpha equals A, the sine of pi over 2 minus alpha is also going to be A. And you can go through this bit of geometry with all of the trig functions, but these co-function identities still make sense when we're dealing with the unit circle as well as when we're dealing with triangles. So they're always going to be true. Okay. All right, let's do just two quick examples, maybe three quick examples of using some of these things that we've talked about today. So some easy ones first, just to be explicit about what we mean. Let's suppose I have that the sine of alpha is equal to 0.517. Then if I want to compute the cosine of pi over 2 minus alpha, we know that it has to be exactly the same number, right? I don't know what alpha is. I don't know what that angle is. I don't know what pi over 2 minus that angle is. But I know if I know the sine of alpha is 0.517, then the cosine of pi over 2 minus alpha must be 0.517. Or if we know, for instance, that the secant of pi over 3, let's do secant of pi over 6, just to make the numbers easier. This has a value of 2. Then we know that the cosecant of pi over 6, which is equal to the, of pi over 3, which is equal to the cosecant of pi over 2 minus pi over 6. Right, if you don't believe me, pi over 2 minus pi over 6 is pi times 1/2 minus 1/6. 1/2 minus 1/6 is 1/3. So I haven't changed anything there. And then we know from our cofunction identities that cosecant of secant of alpha is equal to cosecant of pi over 2 minus alpha. So in this case, alpha is pi over 6. So this has to be equal to secant pi over 6. So that also has to be equal to 2. And so we get that computation, right? This one we can get from the unit circle, but it's just an idea of how these things can be used. Okay, almost done. Let's just look at, go back to what we did in the beginning with these definitions of right angle trigonometry. These will probably be familiar problems. These are typical problems you probably do when you first learn trig. Pretend this is a right triangle. Let's say I don't know how long the side A is, but I know that this angle here is 32 degrees and this side here is 10. If I wanted to know the length of side A, I can use the fact that the tangent of 32 degrees is equal to the opposite side, which is A, divided by the adjacent side, which is 10, right? This is opposite over adjacent. Well, I can solve this equation here for A to get that A equals 10 tangent of 32 degrees. If I put that into a calculator, I get approximately 6.2. Right? It's a long string of decimals, but that's a good approximation. Okay, and this is one of the big uses that trigonometry first had for humans, doing these kind of computations, using the story I always heard historically was how do people divide up land and things like that in days gone by. Or in modern times, you might see, I have a friend who does surveying, and I know they do a lot of their surveying. They do things where they're mapping out homes and properties. And so he's told me he's done things like this. If you've got a building, and suppose you have a drone floating some horizontal distance. So here's our drone. Let's say it's floating at a horizontal distance of 35 meters from the edge of that building. And it can measure what we call alpha, the angle of depression, right? So starting from the horizontal and going down. And let's say that we know that this alpha is 40 degrees. We might want to know how tall that building is, right? Well, we can impose a triangle here. Right? And then it's clear to see that the tangent of alpha is equal to, call this the height of the building, the opposite over the adjacent, 35 meters. Again, we do a little bit of algebra. H is equal to the tangent of, what did I say, 40 degrees, which a calculator gives the approximation 29.4 meters tall. Right, and so we can do these kinds of geometry problems using these really handy rules about triangles, right? They're just really rules about how to, what are the proportions of sides of right triangles. Okay, that's it for this one. It went a little longer than I want, but that's what happens sometimes. Thanks, everybody. I will see you next time.